Today's lesson is going to be a little bit of an extension of what we've already done. In section 3.1, we talked about mean and median and mode. And section 3.2, we discussed sample standard deviation and two ways of finding it, the defining formula and the computing formula. Now, I'm a big supporter of the computing formula, so I recommend that you use that. I just think it's easier with calculations to use the computing formula. Okay, and I'm not going to fuss whichever one you use on test. Okay, so um, but today what we're going to study the descriptive measures for populations and uses of samples. So first and foremost, we discussed earlier all about the sample mean. Now, why do we use a sample mean? Because it's just a lot of times it's not physically possible or financially possible to find a mean of entire population. A lot of times we don't have the data of the entire population. So, but it is good to know how to find population measures when the data is available. So, if you look at this was our definition of the sample mean, and we talked about the formula being x bar equals the sum of x sub I over n, the sum of all the x values divided by the size of the set of data. That's what our sample mean was. But today what we're going to do is we're going to talk about population mean. And in theory, it's going to be the same thing. The notation is a little different though. If you look below, sample mean, we had a lowercase n and x bar for size and mean. For population, you're going to have a capital N for the size of the set. And that little U looking letter is called a mu. A mu. Okay, so keep that in mind. Now, so once we translate those letters, here we go. We get the population mean formula right here. Okay, population mean formula, and notice it looks very similar to the sample mean formula. We're just using a different notation, and it's just a larger size set typically. Okay, it's just a larger size set. So think of it like this: there is only one population mean, because that's a mean of an entire population. There are many sample means because it depends on what sample of the population you choose, and we could essentially if choose a different sample every time if the population is large enough. So there could be a lot of different sample means. So find the population mean of the weight of these soccer players. So population mean again is going to be mu equals the sum of x sub I all over capital N. Now we're looking at the weight of the player, so we're looking at this column right here. And so basically what it's asking me to do is find the population mean. So in other words, find the sum of this. So I need to know what this equals. What's the sum of it? Okay, the sum of all these values. And if you punch that out in your calculator, go ahead and do that. I would pause the video and do it so that you can just get practice doing that. But if you punch that in your calculator, you should get 1125. 1125. So the sum is 1125. How many data values do we have? Well, if you count all those up, there should be 18. There should be 18 values. So 1125 divided by 18 is 62.5 kilograms. This would be our population mean. Now notice, in theory, we did nothing different than what we did with the sample mean. Okay? So don't let, whether it says sample or population, in your mind, that's just some different terminology. We're not necessarily doing anything anything different when it comes to the math of it. Okay, so keep that in mind as you work through this. I know there's a lot of terminology and statistics. Some of you have already mentioned defining formula versus computing formula. They both give you the same answer, so it doesn't matter which one you use. It's just a preference, and I prefer the computing formula. It just seems easier. Same thing here. These give you the same answer. It's just that one deals with population, one deals with sample, and so it's just a matter of syntax here. Okay, it's a matter of syntax. All right, so now if you remember, we talked about when we were choosing samples earlier in the class that we wanted to choose a representative sample so that we could describe the population. That's the goal of any sample that you choose and try to analyze, is you want to get a sample so that you can best describe the population. Well, the same thing. This is the difference in the population mean and the sample mean. If you notice, the big box here is our population, and the population mean with mu is the income of all U.S. households. Now, if we were to pull a sample of 57,000 of these, that would be our sample mean. And hopefully, we pulled a representative sample and a nice even sample, and that would describe our population as a whole. Okay, so that's the sample being pulled out of the population. That's the difference in these two modes of thought. Now, same thing goes with standard deviation. We have a population standard deviation and a sample standard deviation. With sample standard deviation, you had a defining formula, which is the top one on the left, and you had a computing formula, which is the one I really like. Population is the same thing. We have a defining formula, if you notice, and we have a computing formula. Just notice that the terminology is a little different. Notice we have replaced down here in the computing formula and in the defining formula, we've replaced our x bar with mu. We have replaced little n with big N in these situations. Okay, and we have a different variable here. Okay, we have a different variable that represents standard deviation. And so what we have here is we have this. We have, for regular standard deviation, you'll always have an S. Notice. For the sample standard deviation, you'll always have this. Now this is called, it's pronounced, it's a Greek letter, and it's actually pronounced sigma. It's actually pronounced sigma. Okay? So keep that in mind. It's just a different way of writing it. Again, in my opinion, the computing formula down here on the bottom right, this one right here, in my opinion, that will be the easier of the two to work with, just like I mentioned that this one would be the easier of the two to work with, okay? So one is just used for population data, one's just used for sample data. Alright, so some notes. Since we said earlier not to round until the end of computations, remember. If you round before that, it's going to skew your data and mess up your estimation. So in order to do that in these standard deviation formulas, we should replace mu, and my font is messing up, so let me write that. We should replace mu by the sum of x sub I over capital N. Now, if this equals this, so if we replace it, what that is essentially doing is we're replacing it in the formula so that we don't do the division ahead of time. You're going to do the division in the end so that it makes it the computation come out a little nicer. Okay, that's basically what that's called. Now, S squared, standard deviation squared, we called sample variance. Well, sigma squared, because that's messing up with me, sigma squared is called the population variance. It just kind of tells you how much your data is varying from the mean, okay? Just like a sample mean can estimate a population mean, a sample standard deviation can estimate a population standard deviation. Okay, we just want to make sure we have that representative sample there. Just want to make sure we have that representative sample. Now, and let me, that first note that we have up there about replacing, let me say this. If you come out with a nice round mean, population mean, for instance, if it comes out to 20, there's no need to replace because you're not having to do any rounding. It's when you punch the mean out in your calculator and you actually have to round, that's when you want to replace because you don't want to have to do any rounding until the very end. So that's the difference in that, in what I mean by that that particular formula. And we'll talk more about variance a little later, okay? But we won't get into it much in this class, but just know that the standard deviation squared is the sample variance and the population squared is the population variance, okay? All right, so find the population standard deviation of the weight of the soccer players from example 1. All right, well, one thing we need to note, okay? When we divided earlier, we looked at the same set of weights earlier, and if you remember, we found this. Now notice, our mean came out very nicely. We didn't have to round. It was 62.5. It worked out very nicely. So there's no need to replace mu with this in our formula. We're good to go just to use this because there's not any rounding there, okay? So keep that in mind. So again, I'm going to use the computing formula for standard deviation. That's our sigma. That's not a 6, that's a sigma. And our formula, our computing formula for population standard deviation is the sum of x sub I squared all over capital N minus our population standard deviation squared. Okay, this is our computing formula, and very nice. It's very nice, very nice, an easy way to do it. Now, the sum of x sub I squared. Okay. Well, how do we do that? Well, what this means. This is simply asking you to square each weight. Square each weight, so we would square every single one of these, okay? Square each weight and add the results. So what I would do is I would square each of these weights. And then I would add them all up. That would give me the sum of x sub I squared. And if you do that properly for this problem, go practice it. If you have questions, ask your instructor. 70,761. We're squaring each individual weight all the way down the list, and then we're going to take that squared weight and we're going to add up all those values to get 70,761. So that's how we get the sum of x sub I squared. So substitute into our computation formula for standard deviation, and we have 70,761 761 divided by n, and n in this case, if you remember, we said was 18. There are 18 values there, minus the population mean squared, which is 62.5 squared. Okay, 62.5 squared. Punch all that out, and you should get, once you round to one decimal place, right around 5 kilograms. So I would do the division first and get an answer, and then do my 62.5 squared, get an answer, subtract them, and then take the square root. I'm kind of skipping a few steps. I'm expecting you to be growing with this, okay? So with being able to plug these in, this is just plugging it into a calculator. So be careful, make sure you're not making any careless mistakes as you plug these into the calculator. Okay, 70,761 divided by 18, get an answer. 62.5 squared, get an answer. Subtract those two, and then take the square root. I hope that makes sense. That's how I got the 5 kilograms. Now, what does that mean? Well, it means that the population standard deviation is 5 kilograms. So roughly speaking, the weights of all the players fall within 5 kilograms of the mean weight. So roughly saying, we're just saying most of these weights are going to fall within 5 kilograms of 62.5. That's how you would interpret that. Most of the weights are going to fall within 5 kilograms of 62.5, which is our mean weight. Okay? So make sure you can do this. Make sure you can punch this out in the calculator just like we did, okay, using the computation formula. All right, so terminology. A parameter is a descriptive measure for population. And for example, population mean and population standard deviation. A statistic is a descriptive measure for a sample. This should say right here X bar and standard deviation S. Okay, just some terminology. So if you hear me say the word parameter or a statistic, you know what I'm talking about. All right, so standardized variables. Z equals X minus mu over sigma. Okay, this is our standardized variable. Now, why do we do this? We'll think about it. If we're comparing two things that are virtually the same, they have the same mean, the same standard deviation, but they have different numbers, and we're trying to figure out which one's most consistent, or which one's the best buy, or which one's the best gas mileage on the car. We need to standardize. If it's two different kinds of X's, we need to standardize these things so that we're comparing apples and apples. Standardization helps us compare apples and apples instead of apples and oranges. So what this formula is going to do is it's going to take our X values, once we find the mean and the standard deviation, it's going to take our X values and it's going to standardize them into a Z-score. Okay, into a Z-score. And then if we run a lot of different kinds of different data tests into that Z-score, then what we're going to do is once we've transformed it all to Z-scores, we can actually do some actual comparison, because now instead of comparing two different things, we're comparing the same thing. So that's the whole point of using the standardized variable, is so that we're comparing the same thing. So, standardized variable. And letter A says determine the standardized version of X. So remember what the standardized version is. This is the standardized version, but we need to determine it more appropriately. So what I mean by more appropriately is we need to figure out what our mean is and what our standard deviation is. What is mean? What is the standard deviation? So take all your X values, add them up. So -1 plus 3 plus 3 plus 3 plus 5 plus 5. Add them all up, and that should give us what? That gives us 18, it should. And then how many do we have? We have 6. So that should give me a population mean of 3. Well, what about my standard deviation? Well, remember what this asks us to do with population standard deviation. Square all of these first. So if I square them all, that's 1 plus, square them and add them together. So square -1, I get 1. Square 3, I get 9. Square 5, I get 25. So 25 and 25 will be 50. 59, 68. 68 and 9 is 77. And 1 is 78. So for our population, remember it is the sum of x sub I squared, which we just determined is 78, all over n, minus the mean squared. So we just determined this was 78 divided by 6. Okay, 78 divided by 6, that's the number of our population, minus the mean squared. So 78 divided by 6 should give us what? Should give us 13. 3 squared should give us 9. So this is the square root of 4, which is 2. So my population mean is 3. My population standard deviation is 2. So to answer letter A, determine the standardized version of x. Well, we can do that. Z equals x minus 3 all over 2. So basically what this is asking you to do is it's asking you to basically find the formula, okay, so that we can standardize. Now, step 2, letter B. Find the observed value of z for each value of x. So in other words, take these values for x, plug them into our formula, and let's get z. So if I take -1 and plug it in, I get -2. Let me use a darker value here so that it shows up a little better. I get -2. For if I take 3 and plug it in, I get 0. If I take 5 and plug it in, I get 1. Alright, so I found each variable, each value, z value for each x. So now I have standardized this. So find the mean and standard deviation using the population formulas. So if I do that, okay, I'm going to take my population formula here, and so I'm going to find this mean of z. So -2 plus zeros plus 1 plus 1. So if you add up all of these on the bottom row here, it's going to give you 0. So my population mean is 0. Well, if we run this through the same standard deviation process that we did up here, okay, square each one of them, so that's going to be -2 squared is 4, plus 0 plus 0 plus 0 plus 1 plus 1. So that is 6 there when we add all those together. That's going to be the square root of 6 divided by 6, because we have 6 values, minus 0 squared. So really this is just the square root of 6 divided by 6, which is the square root of 1, which is 1. Now, that would be our mean and standard deviation of z using the population formulas. Was it necessary to do this? Well, no, because listen to what the standard deviation does, what the z-score does. It tells you how far away from zero. We're standardizing this. So we're telling you how many standard deviations these things are away from zero. So -2. Notice that -1 gave me -2. So that tells me it's 2 standard deviations to the left of our mean. 2 standard deviations to the left, or 2 standard deviations less than our mean. Zero. Zero tells me it's no standard deviation left because that is the mean. 0 tells me it is the mean. And 1 tells me it's 1 standard deviation from the mean. 1 standard deviation from the mean. Now here's the thing about standardized variables. Okay, here's the thing about these. When you're changing these to standardization, okay, the population mean is always going to be 0, and the standard deviation is always going to be 1. Okay, so because it's always going to be, because we're transforming it into units of how far it is from the mean, how far the standard deviation is from the mean. So this is 1 unit from the mean. 1 unit, 1 standard deviation, I should say, from the mean. Now, to make this make a little more sense to you, think of your number line. We have -1, 0, 1, 2, 3, 4, 5. Now, look up here. What did we find that the population standard deviation was? We found that it was 2. So if we start, this is our mean right here at 3. So if we start at the mean and I go to -1, that's 1, 2, 3, 4. That's 2 standard deviations to the left, or 2 standard deviations less than our mean. See what it's telling us here? That's telling us how many standard deviations it is from the mean. Look at 5. 1, 2. That's 1 standard deviation because the standard deviation was 2. Does that make sense? I hope so. Okay? If not, please feel free to ask your instructors questions on that. Alright, so we've got just a little bit more to do on standardized variables. And you've already heard me say this once. They're often called the z-score. Okay? And basically this is, and I just got finished explaining this with the number line. The z-score tells us the number of standard deviations that an observation is from the mean. It's in units of standard deviation. That's what those zeros, ones, and -2s were in our last problem. They were how many units of standard deviation that value is from the mean. Now, and I've explained this as well already, is a negative z-score means it's below the mean, a positive z-score means it's above the mean. Earlier, we determined that the mean and standard deviation of the weights of the soccer players are 62.5 and 5 respectively. So this was the population mean, and this was our standard deviation. What is the standardized variable? So in other words, write your formula. Write your standardized variable formula here. So remember what it looks like. It's x minus mu over sigma. So this is going to be x minus 62.5 all over 5. So that's how we can take that now, and we can we could change every one of those soccer players' weights into a standardized variable so we can compare them and see how many standard deviations they are away from the mean. So look at Heather Mitt's weight. Heather Mitt is 54. So let's find her z-score. So this is going to be 54 minus 62.5 all over 5. And when you do the math on that, that's going to be -1.7. Now what does that tell us? What does that tell us? It tells us her weight is 1.7 standard deviations below the mean. 1.7 standard deviations below the mean. All right, let's look at Natasha Kai's. Go ahead and plug in 65. Same formula, remember? Punch that out, you get 0.5. That tells us that her weight is half a standard deviation above the mean. Half a standard deviation above the mean. Hopefully that helps you understand how we're using this z-score and standardizing it so we can compare two different things. We're comparing the weight of one person to the weight of another so that we can we're standardizing them so that we can look at them and compare them and see who's closer to the mean, who's farther away, that sort of thing. It allows us to make these comparisons in a standard format. You can't just have different variables all over the place or you wouldn't be able to compare. You like to compare, as I said, apples and apples, not apples and oranges. All right, so some z-score notes. 3 standard deviations rule, and we've talked about this earlier. Almost all observations lie within 3 standard deviations of the mean. So what's that mean in terms of z-scores? It means that almost all z-scores will be between -3 and 3. That's 3 standard deviations from the mean. Z-scores can help interpret relative standing in a data set. A z-score with 3 or more will be greater than most of the other observations. A z-score near 0 means that that observation is pretty close to the mean. Very close to the mean if it's near 0. Okay, so get to work on section 3-4 homework, and hopefully that will hopefully this video will help you. If not, be sure and ask questions. Have a great day.